For our first talk today, I'm happy to introduce Tapasi Ghosh, who is a scientist here at the Green Bank Observatory. She was previously at Arecibo, and today she'll be talking with us about VLBI and the role of large single dishes in very long baseline interferometry. So take it away, Tapasi.
Okay, good morning, everybody. This is basically a single dish workshop, but it's in interferometry at the heart of that. We do have every single dish antennas that take part. So we'll try to give you some ideas to what role single dish telescopes play in there. NRAO runs synthesis workshops, many of you might know. I think it happens alternate year. And if you want to learn more about how to use interferometry and how to make maps, I think ALMA does it too. So I would highly recommend that you attend those summer schools. So this is just a little bit of introduction to that. This is the outline of my talk, Interferometry 101, really very basic 101. And then we'll talk about VLBI and large single dish perspective and what you have to do if you want to include GBT into that, and some scientific result. Next slide. Okay, so here some of you have optical background. So and many of you have done optic labs where you had to play with forming fringes, right? So we go back to the very old Young's double slit experiment, where basically you have a screen and you have a monochromatic light source at the back of it, and you have two pinholes or very small holes. And then on a screen, at some distance away, you can see light, bright and dark fringes. So this is what is called interference pattern. And so the separation, angular separation between the bright fringes is where the D is the separation between the two holes. So you have at some angle theta there. Sorry, I can't point because I don't know if you will see my cursor, but the separation between the bright fringes here is d sine theta is n lambda, and the separation by the dark fringes is d sine theta equals n plus 1 by 2 lambda. So fringe spacing here is lambda by d, and fringe visibility, how clearly you see this fringe, is defined by intensity at the maximum minus intensity at the minimum divided by the average intensity. That's called fringe visibility. So you might have done this in a lab. So take a similar case with radio telescopes here. Here, your two pinholes are replaced by two antennas here, and radio waves coming from at a certain angle here, some angle with the vertical direction. And so we receive the signal and then do the amplification, and you bring them to a device that's called a correlator, where you basically multiply and integrate. What you will see here is also fringes, basically. And now, again, the fringe spacing, if you didn't do anything, as the source travels through this, what you'll receive is your correlation will go up and down. It follow a cosine curve. So here, the fringe, that the spacing there is determined by the geometric delay. What is happening here is basically we're splitting the wavefront. This is called with the same wavefront that comes out of the optical, say, light source. was split into two different wavelets, and those interfered. So that was the Huygens picture of interference. Over here, it's also wavefront splitting that's causing the interference pattern. So the wavefront that has the same phase as the phase of the wavefront at antenna on the right hand side is basically delayed by this geometric time delay divided by velocity of light. So the wavefront here on the left-hand antenna arrives a little bit late, and this delay basically is producing the fringes. So now the fringe separation is now determined by the separation of the two antennas. Now, why do we do this? You probably have seen the angular size of a radio telescope, which is lambda by the diameter of the dish, lambda by d, actually lambda by 1.22d. So, or is it 1.22 lambda by d? That is the angular resolution of a single dish radio telescope. That's why as you go to, that's why it's a big dish, gives you more sensitivity, but it also has narrower beam than a small antenna. Now, if you want higher and higher spatial resolution, you need much bigger antenna. So green band gives us at L band 9 arc-minute resolution. Bigger than that, you go to Arecibo. It has limited sky view, but it gives you 3 arc-minute beam. Fast in China will have much smaller beam. But what do we do even if we need even finer resolution on the sky? So what we do then is we put tiny antennas far apart, and now your resolution is determined by the separation of the two antennas. So, and then in normal interferometry, what we do is, this is called the cosine channel. This fringe visibility is a complex quantity. Now, if you go through the math, you will see it's a complex quantity. We will do a little bit, but we'll really not dig deep into the mathematics of it. But normally what you do is you put another channel and insert an artificial 90-degree phase there, and you determine the sine channel. So basically you're determining the bright fringe as well as the dark fringe, so-called dark fringe. So you're getting a reception of the correlator both at the bright fringe and at the dark fringe. And out of that, then you can construct a complex visibility function. So, okay, so let's go to the next slide, please. By the way, if anybody has any question, then stop me at any point. Not only me, we have lots of people here. They know all these things very well, so we can all try and answer your question. So now, tracking a source across the sky. So here what we have done is, two antennas are now called T1 and T2. So they could be oriented at any angle. Now, as the source goes across the sky from rise to set, this projected baseline basically traverses an ellipse on the surface, on the plane, a plane of the observation. Okay, so that's the baseline vector, and basically that's what is determining your resolution. And now, this baseline vector can have any orientation. So normally what we do is we take a east-west and a north-south projection, two components of the baseline vector. So the east-west projection is called EU, and the north-south projection is called V. So no, stay on that one, please. Yeah, just a little while.
Sorry, Tapasi.
Right, no problem. So you will hear in interferometry all the time, that's UV plane. We need good UV coverage. We need good UV plane. We need visibility as a function of UV. So you will hear all the time this term UV coverage. So that's nothing but the two components of the baseline vector and what it is doing on the plane of observation. It also determines the your array design, because I'm showing you just 2 antenna here. Now, ideally, VLA has 27 antennas. ALMA has how many? 60? I forgot. So loads and loads of antennas. So each of them will give you a baseline vector here, and they will have their projection. So basically what you're doing, you're constructing an aperture that's covered by this UV coverage. So people who design an array, they really pay a lot of attention. And why that is, we'll come to that also in a minute. Okay, so usually what you have to do with this fringe visibility is also a so-called Hermitian vector. That means you only have to measure EUV at 2 positive values of U and V, because its complex conjugate at the value of visibility at minus U minus V is equal to U and V, value of visibility at U and V. So you only need to measure the positive UV values. So you can cut down some measurements. All right, let's go to the next slide. Okay, so here I'm talking about an extended source. So far, we only talked about like a point monochromatic sources case, just 1 point light source. What happens if the source has some structure? I mean, our goal is to map the source, right? So obviously we're after basically mapping the source structure. So now on the sky, you see this little omega here. So this is a strange looking source up here, gray color, and you see an omega vector there. The 2 antennas are pointing at 1 point in the source, which is called the phase center of the source. Now, related to that, omega is a little vector. Now, as you might have seen that so each point in the source will create its own fringe pattern on the ground. And what you will observe is basically a vector sum of all those fringe patterns, right? So what we will basically observe, so fringe pattern coming from a point here will have a little bit of phase shift, a little bit shifted in terms of your visibility pattern. So you have one set of visibility pattern from 1 point in the sky, and then next point in the sky will have another fringe pattern which might be slightly shifted. What we will observe is a vector sum of these two. Okay, so this is what this equation is. So it's basically observed visibility is basically vector sum of visibilities coming from all points in the source. Now, if you look at this very carefully, you will see that this is nothing but the Fourier transform of the intensity distribution on the sky. So what is visibility is measuring is for one baseline value, we're measuring a Fourier component of the intensity distribution on the sky. So then we can apply Fourier analysis, and what we can do is we can inverse Fourier transform, with all. Of course, to do that, we need to measure visibility at various values of B, because now we're going to invert this equation. So we measure visibility at various points of baseline vector, and do a Fourier inverse transform, and then we can get the intensity distribution of the sky with very fine resolution, which will be determined by your UV coverage or your synthesized array, not by the individual antenna. So if you got just this much, I've done my job, okay, for basic 101, interferometry 101. And there's a lot of mathematics, a lot of technique. As somebody once said, that interferometry is really an art. It's not really a science, it's an art. And I'll show you some demonstration of that in a little while. So let's go to the next slide, please. Okay, here's a little bit of art. So, so what is what's the shortcoming? What's the bad news? Good news I give you already. The bad news is we often don't have ideal situation. Okay, before we get to that, this is some examples of what is the image and what's the visibility, what is the visibility plane. So this is a point source, and its visibility amplitude is basically same everywhere we measure. So this is its visibility as a function of U and V would look like. Sometimes we plot visibility as a function of the baseline amplitude of the baseline vector. That's one plot, and it's easy to see. You see that with the amplitude of the baseline vector, visibility is not changing. And what does that mean? That means my source is a point source. It's unresolved. Now it's an extended source here, and you can now see beautiful fringe patterns here. And if I basically plot it radially like this, what I'll see is a beautiful pattern here. Like so these are the relations. So this is what we measure. This is what we get to. These kind of plots we basically look at to decide what my structure might be actually. So there's a Fourier relationship between this plane to that plane. Next slide, please. Okay, here comes the art. The problem often is that we don't have complete sample of the UV plane. That means we may not, very often, we do not have all visibility values at all possible baseline values. Basically, even within a box, we don't have all measurements. Ideally, we want that, we need that. So what ends up happening is we take our visibility, we just do a simple Fourier transform, our image looks like this. Is this all real? Most likely it is not. So we call it dirty image. Now, from that, to get to a reliable image, what we have to do is basically take the effect of the incomplete UV coverage out of this map. And that is done by using a method of deconvolution, which is basically takes out the dirty beam, so-called dirty beam, out of this. So what we're measuring here is the source structure convolved with this my incomplete UV coverages effect, which is basically the dirty beam. So we deconvolve this out of that image using a technique called clean. That's not normally people use. And there you go, beautiful double O radio structure of this quasar coming out here. So there's lots and lots of literature. People have worked for years and they developed many methods of all of this. And you'll get to work with real data if you go to the synthesis workshop. Next image. Okay, here are some pictures. Some of you might have been to these telescopes or used these telescopes, but I just show a collection. Of course, the most famous one, VLA on the top left. And then on the top right, we have the Giant Meteorite Radio Telescope in India. VLA is a fantastic instrument where you can actually move the antennas, they're on rail, and you can change the configuration in a way that your beam, you can have same beam size, same sky resolution at different frequencies. And often that is very important. And it led to many wonderful discoveries. And it has gone through upgrades, and now there's a new VLA in the works. So I think there's some talks about that. GMRT is a telescope in India that works up to L band. It's a low frequency synthesis telescope, and there are 30 antennas. It also works very well up to its frequencies. Antennas are not movable, but it is very useful if your project takes you to those frequencies. And then we have very high frequencies, ALMA in the Atacama desert plain, which is weather there is fantastic. So lots and lots of new and wonderful work coming out of that. 66 antennas, each with 16, the distance is 16 kilometers. Okay, Next slide, please. Okay, now we come to VLBI. Now, so far, the examples I gave you, here, all the antennas are actually physically connected. That means cables, or in some other cases, in other countries like Merlin telescope, there's radio link. So the data online brought into a correlator where they are multiplied and integrated as the observation is going on. So those are actually online linked interferometer. Now, in VLBI, the major difference is we don't have to have that link. What we can do is we can record data separately because radio frequencies are low frequencies. So at that point, the hydrogen maser clocks will allow us to have the frequency down conversion done in a very stable way so that we can basically retain the phase of the detected, not really detected, recorded signal. If you detect the signal there, then you ruined it. You can't form interference fringes. You just record the little bit of voltage at each antennas, and then you bring them to a central processor where you can form the correlation after the fact. So that liberates us from the physical limitation of the separation of the two antennas, where you actually have to, by cable or somehow, link the two antennas. So if you didn't have to do that, you can put your antennas way apart across the continent. They have to look at the same part of the sky simultaneously. So you cannot put one here and one in Australia where we don't have common sky. So common sky meaning at the same time looking at the same object. We cannot do that. That is the prime thing. With that restriction, you can put the telescope anywhere, even in space, and that has happened. So that is the basic difference between very long baseline interferometry and connected interferometry. So there are two antennas which are, one is Halka, which was a Japanese telescope, and then the radioastron. So here are more details. So the basic point here is there's no fundamental difference between linked interferometer and VLBI arrays. So let's go to the next one. Well, I just realized I'm running short of time. It might be go over 5 minutes. Is that okay?
Yeah, that's okay.
All right. Okay, I'll hurry through this.
If someone needs to pop out, then they're welcome to, and we'll have the recording available.
Okay, so the most famous dedicated VLBI antenna is the VLBA. This is done by NRO, and there are 10 telescopes. You can see them all around the continental USA, and there's one in St. Croix and one in Hawaii. This is an old picture of the correlation room. Here the data are recorded in different stations. Then the disk pack these days is sent to the central processor in Socorro, New Mexico. I think this is old picture. Right now, all these hardware looks very tiny because it's all done in a more modern equipment. Next slide, please. Okay, so there are other, here we have the other one, VLBA, and in Europe, there's a European VLBI network. There is one in US, and overall, there's also high sensitivity high sensitivity array. This is where the importance of one sensitive antennas come in. I'll talk about that in a very short while again. So here we have VLBA, all VLA phased up GBT Arecibo Effelsberg, that's a 100-meter dish in Germany. So they all form high sensitivity array, and it's needed for certain type of observation. There is a long baseline array in Australia, a Korean VLBI network, and then there is CMVA, which is millimeter range VLBI. That is organized between telescopes around Europe and America. Next. Okay, these are the two examples of space-based antenna. That's the Japanese Halka. It ran from 1999 to 2001. Both GBT and Arecibo participated here. No, I'm not sure about GBT. Arecibo took part. GBT was still being finished, I think, about that time. Here, Radio Astron, certainly GBT did a lot of work here, not only recording data, they also provided tracking the space antenna. Next one. Okay, here comes the main question here. So as I said, so VLBI resolution here is not determined by the size of individual dishes, it's determined by the baseline vector and its size. Okay, here is the VLBI image sensitivity. So this is system equivalent flux density. That means you all have seen what is a TSIS, right? So for instance, at L band, GBT's TSIS is about 18K. Now you need to then see what is how many Janskis will increase the system temperature by a factor of 2. That is the system equivalent flux density, or 18K equals how many Janskis. That number is 2.5 or so. No, gain is 2.5 anyway for GBT. So we can basically, it's TSIS divided by 2. TSIS divided by gain is the system equivalent flux density. So image sensitivity depends heavily on how many antennas you have in your array. The more antenna there are, all equal, then this goes up. Baseline sensitivity, on the other hand, is related to square root of a CFD of one antenna and a CFD of the other antenna. Here comes the importance of a sensitive or a big dish. So even if you have mostly small dishes, if you have one big dish, you see your baseline sensitivity increases immensely. And for certain type of observation, this is very important, that you have very, very powerful baselines. I'll give you some examples in a very short while. This is talking about the normal field of view. Field of view in case of interferometry is determined by many factors. I don't have time to go into that, but big antenna has its own smaller primary beam, so you have to think about that, how that affects your field of view. In VLBI, normally people don't map the entire field of view, they map tiny regions within the field of view. You can do multiple field images in software, but you have to be careful where do you put your tiny region. It is not determined by the small antennas, it's determined by the biggest antenna in your array. Next slide. Okay, there's a very important app. This is on EVN page. It's called EVM Sensitivity Calculator. Everybody uses that, and it has all telescopes, including the VLBA. So you click on the antennas you want to use, enter the actual parameters, and it will give you image sensitivity, baseline sensitivity, all the relevant parameter you need for your proposal writing, and determining what array you want for your scientific purposes. Next. Okay, here is a table that quickly shows you the impact of the big antennas on a VLBI array. Here, let's just go through one quick example. Well, I made this slide for Arecibo, but I haven't had time to do it GB plus or minus. So Arecibo doesn't have the millimeter part at all. They go only up to X band, which is 10 gigahertz, and these days, that's another story. But anyway, so just look at these two numbers. EVN plus Arecibo gives you image noise 3.8 microjansky per beam. You take Arecibo out, your image sensitivity gets 3 times worse. Okay, so you will image sensitivity you can recover by spending more time. So now let's go to the next slide. So Here again, summing up, what is the special things you have to consider if you have a big dish in your array. So I mentioned all of this. I think some people have done 200 face centers, and basically what you have to be careful about. I'm sorry, I'm going to skip more about this particular array. Let's go to the next one. Okay, so things that you need to consider if you have a large dish. So slew times will be longer for large single dishes. Tiny antennas can go backwards and forwards much faster. Often in VLBI, people observe in so-called phase referencing mode, where you go backwards and forwards from a compact source to your actual target. There are various reasons for doing that. If there's question, I'll talk about that, but let's skip that. So in those kind of observation, you have to switch between sources. So if you're big antenna, you have to worry about how fast you can go backwards and forwards. You need break in the schedule to have pointing and focus calibration. This is very important for GBT at higher frequencies. And 3mm VLBI is becoming very important here. Dave gave you a nice example of that. So, but you have to see that every half an hour you put a calibration time for that. Okay, all right, next one. This is what GBT has. So we have a VLBA compatible backend and a Mark 6, so-called Mark 6 recorder. I'm dropping various names here, I'm sorry, but we can talk endlessly about all of this. But major thing here is we're completely compatible with VLBA. And we take part with HSA, we take part with GMVA, and we can also take part with EVM. Next slide. How do you actually do it then? Is there a separate proposal and dealing with VLBI at GBT? No, you go through NRU's overall proposal submission tool, and you include GBT in there. And if you get time, then you prepare your observing file using a program called SCED, which is controlled and maintained by NRU, Socorro. So you basically make a schedule for your observation. You just submit it to a general place, and then it gets taken care of from there. You don't actually be present for your observation, because all observations are done same way. Your typical parameters that may be just right for your observation, those are all specified in this so-called key file, and there'll be somebody assigned to help you out with all of this. So you created it, you put it out into the depository, and then someone will produce a station-based schedule that gets uploaded to GreenBank, and we check these out, and we make sure that things are there, make sure that the hardware is working, and then it's run. For GBT, if you have GBT in your schedule, you have to allow at the beginning some pointing time, about 13 minutes in the beginning. And then if you're doing high frequency, every half an hour, you have to allow for calibration time. That's the only thing when you plan your observation. But when all that is done, you will get fits data in a normal way. How you reduce that, you might already know, or you go to the Socorro's workshop to learn about that. Next slide. Okay, a few quick signs. I think Dave showed you, this is one example where individual baseline sensitivity mattered immensely. This is basically measuring actual distances to Pleiades cluster stars. And these stars are basically microjansky stars. They are in their binary orbit. And the goal of this was to measure actual proper motion across the sky. To measure that, you had to solve out their binary parameters, and so you needed as much sensitivity as possible. This was a dubious case because Hipparcos came along. That's the satellite. They gave a distance measurement which was deviant to all other various measurements over the years. Then Carl Melis from San Diego used VLBI, and his measurement fell here. And then Gaia went up, and Gaia found that the VLBI measurement is indeed correct. Gaia agreed with the VLBI. Okay, next slide. This is FRB. Andrew can talk a lot about this. This is another thing where there's no time to integrate. You know, one way you can get sensitivity is either you increase your bandwidth or integration time. But here, FRB goes in a flash. I mean, it is a flash. So right at that time, you have to detect the source. You need instantaneous sensitivity. So you need high sensitivity array here. Next one. Okay, I'll skip this, but this is basically showing in detailed structure of H1. From H1 absorption measurement, you can work out the AGN structure so well. You know, the obscuring disk is at this angle, and the jet, one jet is penetrating through the obscuring jet, other one is behind the obscuring disk. So all that was worked out using HSA. Next one. Okay, summary. So VLBI provides extremely high angular resolution. We are moving towards ultra wideband, and large dishes are important. Large single dish telescopes with VLBI are invaluable for spectral line and transient source. And one last, very last slide, next one. I really want to mention this. You might have seen this one. This is the image of the gravitational the black hole image, and this was made with Event Horizon telescope. These were the telescopes used, and we're talking about NGVLA, and that's going to revolutionize this field. Okay, I stop there, and thank you.
Great, thank you very much, Tapasi. We can take some questions, but I will also say, let's plan to come back at 11:15 for the observing recap. We'll just go through each group and have a minute or so to say what you observed last night. So if there are any questions for Tapasi now, feel free to unmute yourself.
Okay. Hey, I spoke very well, I think. Sorry, I kid you not.
So
Sorry.
just, you mentioned the NGVLA yesterday. I think it was Dave or maybe Karen who mentioned that right now the plan for the NGVLA is to put a station in Green Bank.
Seems to be going that way, yes. Yeah? Do you have a question related to that?
Nope.
Oh dear.
I just wanted to point that out too.
Right, yeah. NGVLA will have basically, I haven't read up too much about it, but their core will be somewhere in, in New Mexico, Arizona, and that area, northwest, sorry, not northwest, but southwest. And then they will have, it'll have kind of a spiral structure. The array configuration is very, very interesting. So it is a combination of, none of these will be connected element because they are maybe the inner core might be connected. Others are not connected element, of course. I think they might use wherever possible. If there's a high data rate connectivity, then some of the data might even go over internet. I'm not sure about that, but they'll have antennas on spiral arms. There's one was originally planned to be near Boston. That's the one that's going to come near Green Bank. But these are still smaller antennas, okay? They are 18-meter antennas. So GBT will still be very, very useful. And then, for things like Event Horizon telescope. So it will be, and GBT as a single dish, of course, has lots and lots of usage. But we certainly welcome having an NGPLA antenna right here. There's so much expertise, and it's a quiet place. It makes sense to put it here.
All right, thank you very much, Tapasi. And for everyone else, again, we'll plan to come back not at 11, but at 11:15.
Okay.